Okay, so for this third video, I'm thinking more just a few examples. This is the first of them. Let's say that you have this graph, and this graph, you don't know what it is. It's a function without a name. It's a function without a title. So you can't find what f prime is. But you notice, once again, that the linear behavior, I'd say from about right there to right there, is pretty darn good. That's a very linear graph. You also know that this part is pretty linear. You could say that this part is pretty linear, and I'd say this part is pretty linear. You could probably extend that out right there. So I have like 4 linear chunks. The linear behavior on those pieces are pretty high. We'd probably want to avoid the mins and maxes. I think that those, by nature, those are not linear. So we'd want to avoid the area immediately to the left and immediately to the right of the curve, where it curves up or down. But the behavior between, those are pretty linear in nature, especially if you can break it up into 2 separate pieces. Like from there to there, that's pretty linear. From there to there, that's pretty linear. From there to there, we've got 3 linear chunks. So we don't know what the graph is. We found it in some mathematician's textbook. But we're, for whatever reason, particularly interested in what's happening around these 2 negative quarter parts. F of negative 1/4 is 0.15. F prime at negative 1/4 we've been able to ascertain through whatever means that the derivative there is equal to 3.4. Well, that means that anything around negative 1.4, or excuse me, negative 1/4, not 1.4, excuse me, negative 1/4, anything around that value is, we can use linearization. So then I must ask you, what is f at 0.2? And certainly we have all the information we need to do a linearization at f of negative, not 0.2, negative 0.2. Now the reason I can do this is f of negative 0.2 is really, really close to f of negative 0.25. So the linearization here is possible. Now, do we know how much the error? No, not necessarily. We maybe need to ascertain that from the graph. But if we feel like, okay, for the purposes of our research, for the purposes of our methods, some error here is reasonable, then we can use 0.25 negative to estimate what 0.2 is using linearization. So step 1, find L of x. And I will pause. You can pause the video here if you want to find it on your own. So L of x, I'm just going to use the point slope version. F prime of a, x minus a, plus f of a, which is just point slope of a tangent line. So now we're going to plug these values in. L of x equals f prime at a. Well, f prime at a is 3.4. Okay, and then x minus a. Now we have to think, what is a? Remember, a is where we centered the tangent line around. We centered the tangent line around negative 1/4. So my a is actually 0.25 accordingly. And then f at a is 0.15. So when I simplified it down, it looks like I have L of x equals 3.4x plus 1. So now we can use this to find what L of negative 0.2 is. By just plugging it in, I'll give you a moment. You can pause. And that value is 0.32. Okay, so that is an example of how you might use linearization in a graph unknown to approximate a value for a function that you might not have all the information for. And if you take the last video, also one that is just ugly or unfortunate, you just have to be really, really conscious of error and whether or not for your purposes the error is okay, if the error is tolerable. The error is something you can work with. All right, second example. We're going to find the cubed root of 27.03 using linearization. and I want to determine the error as well. So to kind of kick this off, I went ahead and showed you the graph of x, the cubed root of x, to kind of show you how linear this is. So the cubed root, where it's changing drastically, may not be linear enough to estimate. You might be really careful about linearization around those parts, but linearization works fabulously for cubed root, because once you get away from 0 and 1 to where the cube root isn't changing that drastically anymore, the behavior is really linear in nature, which means linearization is actually going to do a really good job of estimating this cubed root. So the first thing you have to appreciate in this example is that the function here is x to the 1/3. That's the function that we're looking at. And we're looking specifically where x equals 27.03. That's what I'm trying to find. I'm wanting to find what the value of f of x, or f of 27.03, is when f of x is equal to the cubed root of x. Okay? So the first jump we have to make here is reframing these in our brain to realize, okay, this is just f. This is just x is 27.03 when f of x is the cube root of f, or excuse me, the cube root of x. So we are making that jump. So that means we can use this function to create a linearization, and then use that linearization to find f of 27.03. But the first step, after we recognize the kind of the root function, is where are we going to center it? And we want to center it thoughtfully. Where can I center this linearization that would make this easier, not harder? Because if I have to break out a calculator, that kind of defeats the purpose of linearization. Linearization is supposed to make a nasty function better. So I think about it, and I think, 27.03 is really close to 27. And the relationship that 27 has to the cube root is that 27 has a cubed root. The cube root of 27 is 3. 3 times 3 is 9, times 3 is 27. So now I know that my parent function is going to be this. That's my function that I'm using. And my a is going to be this. I'm going to center it around 27. Okay, so let's clarify. My f now is the cube root, or x to the 1/3. My a is going to be 27. So that f of a is 3, and that f prime of x is 1/3 x to the negative 2/3, and that f prime of a, or 27, I have in my notes as 1/27, and I'll let you check that as you will. Cube root of 27 would be 3, 3 squared is 9, 3 times 9 is 27, so that makes sense. So now I have all that I need for my linearization. So I'm going to shrink this down, put it up in the corner, and recall that L of x is f prime of a, x minus a, plus f of a. Okay, so then L of x, we have f prime of a. F prime of a is equal to 1/27. X, we said a, we're putting it around 27. And f of a is 3. So if I boil this all down, I get 1/27x minus 1 plus 3, which is 1/27x plus 2. And that's my linearization. That's my nice, friendly tangent line. And if I plug this simpler thing into a calculator, I'm going to get the L of 27.03, which is really what I'm after, is approximately equal to 3.001111111. That's what's in my notes. So this value insinuates, or this value tells me, based on my linearization, what f of x is at 27.03. So the question now becomes, now that we have a calculator that can do the cubed root, let's go see what the error is. So remember that the error, I need the actual versus the estimated. So that means I need to know what f of 27.03 is. So you can go ahead and put that in your calculator. I have it written down as 3.001107. So those two values compared to each other, if you put them in error, so remember that's actual minus estimated over actual. Absolute values in the top, and I have approximately 1.33 times 10 to the negative 7, which is really, really, really small. In fact, some might even say, depending on scientific numbers, scientific digits, that's about 0. We're looking at a 0 error. That's really good. There is practically no error using this method. So this method, this linearization, worked phenomenally when I centered it around x equals 27. This linearization may not work as well if I centered it around, say, 0, where it's changing really drastically. And by the way, this isn't even differentiable at 0, but maybe even really close to it, like 0.0001, where it is technically differentiable, but changing drastically. That linearization may not be so good, depending on where we're looking at. So, the point, yay linearization, it works really well when used appropriately. It can be a great tool for estimation, but it's not perfect. Now, as we move on into second semester with Taylor polynomials, we're going to see that we can add on to this linearization at times to come up with a better estimation. And then we can eliminate some additional error as well.